is actually an ensemble that was invented to describe a situation in which both the energy and the number of particles are not constant, okay? So in practice, you're considering a system like this one. You have some big volume, and then in this big volume, you divide it into two parts. You have one small volume with a V1 with a number of particles and 1, and a bigger one and V2 with a number of particles and 2. This is much bigger, and both the energy and the number of particles can fluctuate, can be exchanged between the two subvolumes. Overall, the entire system is, of course, thermally isolated, but who cares? And what we are interested in this is in describing the statistical mechanics of the small system. So V is equal to V1 plus V2, and N is equal to N1 plus N2. And we're interested in the statistical mechanics of the entire system. Let's imagine it's a gas, just for simplicity. So Zn, the partition function for the entire system, is going to be equal to the integral dq dp over h to the 3n n factorial e to the minus beta h qp, where hqp is in principle, as usual, the sum of two terms, the Hamiltonian H1 of the particles in the volume 1, and the Hamiltonian H2 of the particles in volume 2. So in practice, we can rewrite this as integral dq dp over h3n n factorial e to the minus beta h1 plus h2. Now we have to incorporate in this expression the fact that the number of particles can fluctuate between the two subsystems. So the number of particles in 1 and 2 is not fixed as in the case of the canonical ensemble, but can change. So in practice, this means that we can rewrite this expression as follows. This is the sum over all possible configurations N1 and N2, such that N1 plus N2 is equal to N. Then here we have to put a factor that describes the number of ways we have to put N particles and divide them into two subsets, N1 and N2. And this is the famous binomial factor. So it's N factorial divided by N1 factorial N2 factorial. And then we have the same thing as before, dq dp over h to the 3n n factorial e to the minus beta h1 plus h2, where it is understood that now there are n1 particles in volume 1 and n2 particles in volume 2. Here in the previous expression, the number of particles in volume 1 and 2, of course, could fluctuate, could change. Once we rewrite things in the way in this bottom line, then the number of particles in 1 and 2 is fixed. So in practice, this means that I can rewrite in a better way this expression as follows. Well, first of all, I can simplify this n factorial with that n factorial. And then I can rewrite better this expression as follows. This is the sum over n1 from 0 to n, and then integral dq1 dp1 over h to the 3n1 n1 factorial and then integral dq2 dp2 h to the 3 3n2 n2 factorial e to the minus beta h1 plus h2, with the understanding that n2 is equal to n minus n1. And now this I can rewrite as follows. This is equal to the sum n1 from 0 to n integral dq1 dp1 divided by h to the 3n1 n1 factorial e to the minus beta h1 times the integral dq2 dp2 h to the 3 n2 n2 factorial e to the minus beta h2, with the understanding that n2 is equal to n minus n1. So this expression here can be seen as the partition function of system 2 with n2 number of particles, right? So what I discover after this discussion is that this is equal to sum over n1 from 0 to n integral dq1 dp1 over h to the 3n1 n1 factorial e to the minus beta h1 z of n minus n1, and this is equal to Zn. Now, if you look at this expression, this implies the following. It implies if I divide both sides by Zn, this implies that the sum over n1 from 0 to n of the integral dq1 dp1 over h to the 3n1 n1 factorial. All right, no, let me do it this way. Times 1 over h to the 3n1 n1 factorial e to the minus beta h1 z of n minus n1 z of n is equal to 1. But now, notice the following. This expression here can therefore be interpreted as the probability to have n1 particles in volume V1 in probability density in the neighborhood of dq1, dp1. Okay?
Sorry, Professor.
Yes.
How did you get that expression in red? I lost
I
that point.
just took what is written up here and I divide both sides by Zn.
Okay.
So in other words, I take this and I put it down here. You see?
Yes.
All right. So this is the probability distribution to have. So let's try to simplify this probability density in some way. Well, the only expression that is a bit complicated here is this ratio, Z of n minus n1 divided by Zn. So let's see how it should look like. So Z of n minus n1 divided by Zn, by definition, is equal to e to the minus beta. And then I have the Helmholtz free energy of n minus n1 particles in the volume V minus V1. And then the free energy of n particles in the volume V. Well, now I use the fact that n2 is much, much bigger than n1. And therefore, yes?
I don't get the expression you just wrote.
Well, so this is related to the fact that Z is equal to e to the minus beta f, as we know.
Oh, okay, thank you.
Okay, so now I use the fact that N1 and V1 are much, much smaller than N and V. And therefore I can do a Taylor expansion here in N1 and V1. And I will get e to the beta N1 df dn plus V1 df dv. Okay?
So, Professor?
Yes.
Where is the minus sign, where is it?
Well, because you see, when I do the expansion here, I have a minus sign, right? So I will get df dn minus n1. So here there will be a minus, but there is a minus in front, and this minus goes with this minus. You understand? You see? Yes or no?
No, not really.
So look, let's do it for f v minus v1 minus f of v. So this is equal to minus v1 df dv, right?
Yeah.
So therefore, when you take fn minus n1, v minus v1, f of n and v, this is equal to minus v1 df dv minus n1 df dn. And now you see that, but there is a minus sign here, and the minus sign eats up these two minuses. So that's why you get a plus. Clear now? Is it clear?
Okay. Okay.
Okay.
Yes, yes.
Good. So, yes. So then now by definition, this is equal to e to the beta n1. dF dN is the chemical potential, mu, minus beta, and minus dF dV is the pressure. So minus beta V1 P. So, okay, that's because dF dN is mu, and this is minus P. Okay? All right. So therefore, what I discover if I use this expression is that my probability density is e to the h to the 3n n factorial, e to the minus beta h, and then I have e to the beta mu to the power n, and then e to the minus beta v times p. So usually people call this expression here e to the beta mu. This is called fugacity. And the letter people use to write it is z, little z. Now, it's a problem because this little z is being used also for the coordination number and many other things, but you have to get used to this. I mean, there are just a few letters and too many concepts in physics. So frequently different letters are being used for the same object. Sorry, frequently the same letter is being used for different objects. So overall, this is equal to 1 over h to the 3n n factorial, e to the minus beta h, and then z to the power n, and then e to the minus beta vp. Now, the fact that this is normalized to 1, so sum over n integral dq dp of rho is equal to 1 implies the following, that the sum over n integral dq dp over h to the 3n n factorial e to the minus beta h times z to the power n is equal to exponential of PV over KBT of beta PV. Now, this fact leads us to define this sum, to call this sum the grand canonical partition function. Now, I don't know how to write, which letter to use for the grand canonical partition function. So I will use this Z that is supposed to be a calligraphic Z, if written by a computer. Let's call it a fancy Z. But we will understand from the context what it is. Now, the fancy Z is the sum over n of Z to the n, little z to the n, multiplying the canonical partition function Z with n particles. Okay, so this non-canonical partition function in principle is a function of the fugacity, the volume, and the temperature. Now, why is it a good idea to define the non-canonical partition function? It is a good idea because if you are able to compute the non-canonical partition function, then the log of z is equal to PV over KBT. And you see that this is practically like telling you, if you're able to compute the log of the non-canonical partition function, you will be able immediately to get something like an equation of state for your system, because you remember that this ratio PV over KBT is exactly what appears in the it's exactly what appears in the equation of state of the ideal gas. Yeah, please, there was a question. Was there a question?
Professor.
Yes.
Actually, I don't get actually how you define the partition function again.
How I do what?
How you define the partition function?
Fine. Well, you know, the definition is arbitrary, right? So in this case, I'm defining the partition function by this equality. Now, why I'm defining the partition function by this equality? Because I know that if I perform this sum, I will get this exponential. And therefore, I know that the log of this grand canonical partition function, so this is my grand canonical partition function. Let's write it. Grand canonical partition function. So while the log of the canonical partition function was giving me the Helmholtz free energy, the log of the grand canonical partition function is giving me the ratio PV over KBT. And this ratio is important because, for example, for the ideal gas, we know that PV over KBT is equal to N, right? Is equal to the number of particles. So this is the equation of state for the ideal gas. So you see, this expression has the structure of something that could tell us if you're able to compute the grand canonical partition function, you could get something like an equation of state for your system. So that's why it is useful. You see, it's an arbitrary definition. Yes.
So my question actually is how do you get the rho, and how from rho you get the partition function?
Well, the rho, I defined it here, right? So here I said, from this expression, from this one, if I divide everything by Zn, I get that the sum of this stuff, sum and the integral of this stuff, is equal to 1. And therefore, whatever is in this box, I define it as the, whatever is sitting in this box, I define it as the probability density rho to have N1 particles in V1 in the neighborhood of dQ1, dP1. Then I found an expression for this ratio. I said rho is equal to this. Right? And now rho is normalized to 1, which means that this means that the sum over n integral dq dp over h to the 3n and factorial e to the minus beta h zn e to the minus beta vp is equal to 1. And then what I do is I take this e to the minus beta vp, I take it on the other side. And I obtain this expression here. Then I say, okay, so you agree with this, right?
Yes.
And now I say, okay, since I obtained this expression, I obtained that this sum and integral is equal to e to the minus vp. Let me now define grand canonical partition function, this sum over n zn little z to the power n. Why? Because if I'm able to compute this object, I take the log and immediately I will have the ratio PV over KBT. And having the ratio PV over KBT means practically that I will be able to write an equation of state. Okay?
Okay.
In other words, the connection between macroscopic world and microscopic world in the microcanonical ensemble was happening at the level of partition, at the level of the entropy. So the log of the total number of states or whatever was equal to the entropy, the Boltzmann formula. For the canonical partition function, what I have is that the log of z is equal to minus beta times the Helmholtz free energy. So this is my connection between thermodynamics and statistical mechanics. For the canonical partition function, the connection is the log of the grand canonical partition function is equal to the ratio of PV over KBT. Therefore, if I want to compute an equation of state, I better use the grand canonical formalism. If I want to compute the Helmholtz free energy, I better use the canonical formalism. If I want to compute an entropy, well, I can use either the canonical or the microcanonical formalism. It depends on what I want to do, but at the end of the day, the three of them are going to be equivalent in the thermodynamic limit, as we will show in a second. Okay? So by the way, you see that the fact that PV is equal to KBT over KBT is equal to n means that at the end of the day, we obtain the grand canonical partition function as a function of z, but we need something that is a function of the number of particles to write an equation of state. So how do you write the number of particles in the grand canonical formalism? The average number of particles is equal to the sum over n Zn and Zn divided by sum over n Zn Zn. And this is nothing but Z d Z Z. So is the Z, the fugacity, times the derivative with respect to the fugacity of the grand canonical partition function. Okay? You agree? All right. So now let's see how this works for the ideal gas. Now, so for the ideal gas, we essentially have to compute the grand canonical partition function, which is equal to the sum over n from 0. Well, so in principle, in the total big volume, we would have a finite number of particles. But in practice, let's take the big volume to be infinite. So let's sum all the way to infinity. Doesn't really matter because essentially most of the contributions to this partition function are close to the average, as we will see in a second, average number of particles. And now the canonical partition function is something that we already computed. Zn is equal to 1 over n factorial times v2m kbt to the power 3/2 divided by h cubed to the power n. Well, then substituting here, we get sum over n from 0 to plus infinity, 1 over n factorial. And then I have v times z times 2m kbt to the power 3/2 divided by h cubed to the power n. And now this is equal to, well, this is just an exponential, right? This is exponential of v times z 2m kbt to the 3/2 divided by h cubed. Now, it's very important that this is an exponential of, that is linear in the exponent. Why? Because now, if we compute the average number of particles, which is z dz of the grand canonical partition function, you see that this is nothing but v. Of log of z. Well, this is nothing like but v times z times 2m kbt to the power 3/2 divided by h cubed. In other words, what I wrote up here is nothing but exponential of n bar. You agree? But
Sorry, Professor.
yes.
I didn't get why n bar is equal to z dz log of z.
Sorry, you didn't get why?
N bar is equal to z dz log of the capital.
Oh, that's because of what I wrote here, right?
Yeah.
So n bar is equal to the sum over n, z to the power n times n zn divided by this, right?
Yes.
So let's now do this derivative. Z dz log of z. Oh, sorry, it's a log here. So let's do this derivative. Yes. Okay. So this is, the following is So is Z dz of the log of sum over n Zn Zn. This is equal to, so if you do this derivative, is equal to Z times dz of sum over n Zn Z to the power divided by sum over n Zn Zn. Now I take the derivative, I obtain that this is Z sum over n. I will have n times Z to the power n minus 1 Zn divided by sum over n Zn Zn. And now I multiply by Z and obtain that this is equal to sum over n Z n Z under sum over n Zn partition function. So you see, when I take this derivative, it's identical to what I wanted.
Yes.
Okay, so you see how it works. All right, so let's erase this. All right, so you see that therefore my grand canonical partition function is equal to exponential of the average number of particles, but this is also equal to exponential of PV over KBT, as we already know. And therefore, this expression implies that the equation of state for the ideal gas is PV over KBT equal to n bar, which is what we wanted. Okay? All right. Yes.
Zn is from the previous lecture, right?
Which?
The form Zn, the partition.
Yeah. This one we calculated some time ago. See, some lectures ago. Okay. All right. So now we are facing a different problem. The problem is to figure out, again, the equivalence of ensembles. So in order to prove that the canonical ensemble was equivalent to the microcanonical ensemble, what we have shown is that in the canonical ensemble, the probability distribution corresponding to the canonical ensemble is peaked around some average energy with energy fluctuations that actually scale as relative to the average as 1 over square root of the number of particles. And therefore, in the thermodynamic limit, the ratio of standard deviation to average goes to 0. And in practice, you have a strongly peaked distribution around the average, which is exactly what you're supposed to have in the microcanonical system, in which the system has a definite energy. So this property that the fluctuations are small is what defines in the thermodynamic limit the equivalence of the canonical ensemble and the microcanonical ensemble. It is evident that if we want to prove that the grand canonical ensemble is equivalent to the canonical ensemble in the thermodynamic limit, what we have to prove is that the fluctuations of the number of particles are small in the thermodynamic limit. So in order to prove this, we have to proceed as follows. So you see, the average number of particles is equal to z dz log of z. This we already know. Now we need to compute the fluctuations. So which is n squared average minus n average squared. And well, this can be obtained by, I'll let you prove the following identity. That if you take z dz of n bar, then you obtain exactly the fluctuations. Okay? So in other words, in order to compute these fluctuations, we have to compute z dz of z dz log of the Grand canonical partition function. And that's it. Okay, so now, how do we proceed? Well, first of all, the derivative with respect to z of something can be written as the derivative with respect to the chemical potential, dz, d mu, just changing variables. And dz d mu is equal to 1 over beta z times d mu. Therefore, when you see something like z dz of something, this means that this is equal to 1 over beta derivative with respect to the chemical potential. Okay? Just changing variables. Therefore, what I wrote up here means that dn squared, which is equal to n squared average minus n average squared, is equal to applying twice this to log of z. So in other words, is kBt squared times the second derivative with respect to the chemical potential of log of z. But log of z is PV over kBt, right?
Professor,
Yes.
in the second last line, where did you get 1 over BZ?
Well, this is just from the definition of z. Z is equal to e to the beta mu, right? So if you take a derivative of z with respect to mu, this is equal to beta times e to the beta mu. So is equal to beta z. And now you see that. Okay?
Okay.
Okay. All right. So, but now the only thing that might depend on the chemical potential here is the pressure. So therefore, what I obtain from this expression is kBt times the volume times the derivative of the, with respect to the chemical potential of the pressure. And now I want to rewrite this expression in terms of the compressibility. Well, first of all, already from this expression, you see that the fluctuations are actually extensive because they are proportional to the volume itself. But to see it better, let's rewrite everything in terms of the compressibility. So in order to rewrite everything in terms of the compressibility, I have to remember a few things. Number one is the following. First of all, the pressure is equal to minus dF dV. And second, the chemical potential, as we already said, is dF dN. Now, F is the Helmholtz free energy, is an extensive quantity, therefore I can write it as N times a free energy density F. Therefore, the chemical potential, if I put this expression in here, the chemical potential is equal to F plus N dF dN. Right?
Can you repeat what is small f?
Small f is the free energy density. Is F divided by N free energy density. Okay?
Yes.
Okay. So now I can change variables here, introduce another variable which is the specific volume, V over N. And if I change variables in these derivatives, I will discover that this is nothing but this. In order to obtain this, you have to just change variables. All right, so this is the expression for my chemical potential. Now, the pressure P was dF minus dF dV. Well, this is simply minus the little f little v, because I divide both in the numerator and the denominator by f, and that's it, right? Therefore, dP d mu, I can write it as follows, as dV d mu dP dV. But now dV d mu I know how to calculate, because this is like, if I take d mu dV, look at this expression here. D mu dV is dVf minus dVf minus v d squared V F. Okay? And therefore, I obtain the following, that this is equal to 1 over minus V d squared Vf. And then I have df dv, which is equal to minus d squared Vf. So the minus goes with the minus, this d squared goes with this d squared, and I have 1 over V. So this was the first derivative. In order to sort out my problem, I have to compute the second derivative. So d squared p d mu squared is equal to d mu of 1 over V, which is equal to minus 1 over V squared dV d mu. This is equal to, again, I use what I wrote down before, plus 1 over V squared times 1 over V d squared Vf. And this is 1 over V cube d squared Vf. Now, or in other words, if I remember that what was the expression for P, so P is df dv, this is equal to minus 1 over V cube dv P. But now, what is the compressibility? The compressibility, Kt, is defined as follows, is minus 1 over V dV dP. This is the definition of compressibility, of isothermal compressibility. I can rewrite it in terms of specific volume, and I get 1 over little v, 1 over dP dV. And therefore, you see up here that what I have here is nothing but minus 1, is 1 over V squared times the isothermal compressibility, Kt. Therefore, what I discover now is that my fluctuations of the number of particles are equal to kBt squared times the volume, kBt times the volume, times d squared mu p, and this is equal to kBt times v times 1 over little v squared times the isothermal compressibility. Just a second. Yeah. So this is trivially equal to kBt times the number of particles divided by the specific volume times Kt. So what we see from this expression is that the fluctuations in the number of particles is proportional to the number of particles themselves, and therefore the square root of delta n squared divided by n is going to go like 1 over square root of n, and therefore in the limit of n going to infinity is going to go to 0. So in practice, this implies that the number, the grand canonical ensemble is equivalent in the thermodynamic limit to the canonical ensemble, as we expected. All right, so now that we know everything about the canonical and grand canonical ensemble, we will start a part of our probably the most complicated part of this course. So up to now, all calculations were easy, all concepts were simple, everything was nice and doable, and nothing was complicated. Now for a couple of lectures, life is going to be tough, okay? Because what I would like to do is to do with you a calculation using a grand canonical ensemble and a canonical one, showing you how to use statistical mechanics to obtain the equation of state for a non-ideal gas. So up to now, we have always been doing either simple models on a lattice or mean field theory, or for what concerns particles in fish space, ideal gases. Why? Because we were not able to deal with interactions. And now what I would like to do is to deal specifically with interacting systems.
Professor,
Yes.
I mean, are we reaching the last chapter, like the cluster expansion or something?
Yeah, we are doing that.
Actually, before that, can I ask you like several things in the previous lecture, like
Yeah, you can.
in the mean field theory? Actually,
if everybody agrees,
I don't
so
know.
everybody, is it okay for you if he asks questions about everything else? All the others. You want to have a question session for this 15 minutes? 20 minutes? Hello?
Sure.
Okay, good. So please go on, ask me questions. Yes. So about mean field theory, what was the question?
Yes, so actually I don't really understand the part where you are actually discussing about the magnetization, the ferromagnetic phase, and the graph itself, and of course
This one? Which one? Here?
Yeah, that one, and also the part where you get the critical exponent. I mean, I don't really get the story behind it.
So you understand that we have to solve self-consistently for the magnetization n, right?
Yes, I understand that much. I mean, I follow the derivation and I get to that point, and after that, I don't really understand what's going on, actually.
Well, so we have to find the solutions to this equation, right? So how do we find the solutions to this equation? Well, analytically, it's not possible, right? This is not an equation that you can solve analytically.
Yes.
So let's do it graphically. Let's plot m, which is just a linear slope, like this one, right? And we have to plot the tangent hyperbolic of beta times j times n. Okay? Now, this tangent parabolic, how do you plot it? You know that it goes to plus and minus 1 at plus infinity and minus infinity. The only relevant parameter that you have is the slope of this curve at m equals 0. Right? This slope is
Which slope, sorry?
the slope of the tangent hyperbolic at m equals 0. Right?
Okay. Okay.
Just a second. So, tangent hyperbolic beta jm. There is a z somewhere. Just a second. Beta j z m. So the slope has slope beta times j times z times j at m equals 0. Okay, so this is the slope. Now, what does it mean? It means the following. Let's plot everything. So this is plus 1, this is minus 1, and this is the linear function. So this is m. So the slope can be smaller than 1. If the slope is smaller than 1, this curve will look like this. If the slope at m equals 0 is smaller than 1, the curve will look like this. And therefore, these two curves will intersect only in one point, at m equals 0. You agree?
Yes.
So only one solution when the slope is smaller than 1, which means that z, jz divided by kbt is smaller than 1, or in other words, that the temperature T is larger than J times Z over KB. Let's call this TC. So when the temperature is larger than this quantity, there is only one solution. Okay? Only one solution. When the temperature is smaller, in other words, when this slope coefficient is larger than 1, there's more than one solution, right? Because in that case, the curve would look like this. And it has three solutions. It has three intersections. Here, at m equals 0, and at these 2 points. Okay? Three solutions.
Yes.
Now, which one of these three solutions should we choose? Can you tell me? Which one? We have an equation that has three solutions. Which one should we choose?
The one that satisfy all requirements.
And what are all requirements?
The one that's smaller than 1, greater than 1, and at m equals to 1, I suppose.
I didn't get you. So what is the requirement?
Maybe at the intersection. I don't know. I'm not sure. Sorry.
So what could be, what are the requirements that the solution should satisfy? Can someone else tell me?
I think is that m is equal to tangent hyperbolic.
Yeah, well, okay, that's one. Of course, it's the,
Yeah,
if you
so
are a
it's,
solution, of course, you satisfy that. But in order to decide whether which one of these three solutions to this equation I have to choose, which requirement should I satisfy?
It should be between the m plus and m minus.
Well, so
Find
but
if it's a minimum or I think
it's a
major.
minimum of what?
The second derivative of the free energy.
No, okay, the second derivative of the free energy should be positive. In other words, it should be a minimum of the free energy. Okay?
Yeah.
So in order to decide which one of these three solutions to pick as the physical state of your system, it should be a minimum of the free energy, right? So this is the, as we have seen a long time ago, minima of the free energy are the equilibrium states. So that's why I calculated the free energy. I did it here. And I've shown you that the second derivative is positive for these two solutions. This one and this one. Well, for this one is negative. So for, let's call this n plus and this n minus. For n plus minus the second derivative of the free energy is positive, and therefore they are okay. But for m, for 0, the second derivative is equal to 0, sorry, is negative, and therefore this is not okay because it's a maximum. Therefore, I cannot pick for these temperatures, T smaller than Tc, I cannot pick 0 as a solution because it does not satisfy the basic requirement of being a minimum of the free energy. It is actually a maximum. So out of these three solutions, I have only two solutions that are good, m plus or m minus. So in other words, people say I spontaneously break the symmetry because the system will be sitting in one of them, either m plus or m minus. And it's going to have a finite magnetization without a magnetic field. Now the critical exponents. Well, so here, what I'm plotting is one of these two solutions, let's say m plus,
Oh, wait,
as a
wait.
function.
Uh,
Yes,
Can you repeat the part of the minimum of free energy? Why the second derivative?
well, so if you have a function and you find a minimum by setting the condition of the first derivative being equal to 0, what is the condition? Sorry, you find an extrema. The extrema by setting the first derivative equal to 0. What is the condition to have a maximum or a minimum? A maximum is when the second derivative is negative, and a minimum is when the second derivative is positive.
Actually, I mean the physical meaning of that.
Well, so if you have, so we are looking for minima of the free energy. Which one of these solutions is a good solution is decided by the following fact, that a good solution is a solution that is also a minimum of the free energy. If it's not a minimum of the free energy, it's not a good solution. And that's why I'm computing the second derivative. Okay?
Okay.
Okay, good. And now I'm saying, okay, suppose that I plot m plus this solution as a function of t. Well, so this is going to be finite all the way to tc, but I know that for t greater than tc, there is only one solution, m equals 0. So therefore, the magnetization, this m plus, is going to 0 at tc. And it's going to 0 in some characteristic way. So what I've done here is I figured out how it goes to 0 by expanding the equation m equal to tangent hyperbolic of tc over t times m, expanding it close to this critical point where the magnetization is small, so I can use a power series of the tangent or of the arctangent hyperbolic. And if you do this expansion, you're able to find these three solutions and to compute these critical exponents. Is it clear now? Did you understand?
Why? Actually, I kind of still don't get the part. Why you? I mean, why do you need to expand near the critical temperature?
Well, that's my choice, right? I mean, why do I expand? Because I want to see how m plus vanishes close to the critical temperature. So that's why I expand.
Oh, okay, okay.
But close to the critical temperature is also the only point where I can do an expansion because I know that my magnetization is small. And therefore I can use a power series using m as small parameter. Okay?
So the solution is like m0 and plus minus 3t to the power of half, right?
Yes.
Which is why you draw the curve to be more or less equivalent to the m times to the minus t to the power of half.
Yes.
Okay.
Yes, that's exactly why I write the curve that way. Are there other questions about this? Or about something else? Since now, I mean, it's impossible to start the cluster expansion. Ask me any question about previous lectures.
Yes, I have a question. Can you
Yes.
re-explain about the hysteresis?
Explain about what?
Using mean field theory to understand the hysteresis.
To understand the?
Hysteresis.
Hysteresis. Okay, so, well, so you remember this figure here, right? So the two are sitting there. So my system is sitting, no, sorry. Suppose that the system is sitting here with this magnetization, right? And now I start increasing the magnetic field. So the system has, I had 0 magnetic field originally, and now I start increasing the magnetic field. So the system has some finite magnetization, positive magnetization. I start increasing the magnetic field. So what happens is that the just a second. So what happens is that these two minima, I have to plot it in a more in a better way. So when I increase magnetic field, what is going to happen is the following. So without magnetic field, I had two nice symmetric minima, like in this figure, Now I start increasing magnetic field. What happens? What happens is that is the following, that this guy starts shifting in this direction, and this guy gets deeper. Eventually it shifts and shifts and gets tinier and tinier, and this guy gets deeper and deeper. Eventually this becomes a saddle. And you have only one minimum in the direction set by the magnetic field. So, yes?
Sorry, is this like the curve you draw before about the free energy to the magnetization, which gives you transition from paramagnetic and from paramagnetic to ferromagnetic?
Yeah, this is free energy versus magnetization. So what I'm showing you is how the free energy changes when you introduce a magnetic field, right?
Right.
And so in practice, what happens is that is the following. You will have two master curves that are, if you're sitting in this maximum and you increase the magnetic field, you will be following one curve. And if you're sitting in the other, you will be following another one. And then what the system does, follows this curve
Yes,
up to some point. Yes?
Actually, I don't get that you have just drawn.
Well, suppose that you're sitting in so suppose that I'm increasing the magnetization, right? And I initially was here. So actually, well, this is all plotted. All these minima should be shifting in this direction, actually. So, but what happens is that your magnetization, if you initially had a positive magnetization, your magnetization will increase and increase and increase up to a certain point, at which you switch at which you stop your magnetic field. If you're sitting here, your magnetization, if you were sitting here and you stay in this minimum, your magnetization is going to follow a different curve. You see?
Yes.
Up to the point in which this minimum becomes unstable. When it becomes unstable, the magnetization changes and goes to the true minimum. Then when you trace it back, is going to follow this one up to a certain point, and is going to do the symmetric thing. So the curve is going to look like this. You see what I mean? What I'm trying to say is the following. If your system initially was sitting here, when they were symmetric, and then you put a magnetic field that favors the opposite magnetization, what is going to happen is not that all the spins will immediately reorient in that direction.
I'm so sorry, Professor, but I cannot hear you clearly.
Can you hear me now? Better?
Yes, now it's better. So can you restart?
So
Yeah, okay.
if your system was sitting here, which means that you had negative magnetization, and then you start increasing the magnetic field, what is going to happen is that it's going to move along this curve, which means it's going to move here, up to the point in which this minimum, this local minimum, which is not the true minimum of your free energy, becomes unstable, becomes a saddle, and then disappears. At that point, the system is going to go to the real minimum, which is this one, and then continue there. If you now turn the magnetic field and start decreasing it, the system is going to move in this direction. It's going to stay in this minimum, and so on and so far. And then everything is going to be symmetric. Then this one is going to be a local minimum, but the true minimum at some point is going to be the other one. So it's going to follow this up to a certain point in which it becomes unstable. Then it's going to jump to the true minimum, continue here, and then if it traces back, it's going to follow this. This is hysteresis. So the value of the magnetization in practice depends on the history of your change in the magnetic field. You understand now?
Yes, Professor.
Yes.
Yes.
So my question is like, so when you're changing the magnetization, the other side of the curves goes down, so it becomes the true minimum, and then
Yes.
you're changing it back, and so such that the true minimum moves again. So you mean that actually the other side of the curves goes down now, and when the other side of the curves goes up. Is that correct?
Yes, exactly. You know, so in other words, I start from a symmetric thing. The guy is sitting here. When I put a magnetic field, this goes down, this goes up. But I'm always staying here until it becomes unstable. When it becomes unstable, I jump and I stay where the true minimum is. Then I change direction of change of the magnetic field. In that case, if I change direction, this starts going up and this starts going down. So I move in this direction. At some point, this guy will become unstable. I jump down and I move here. You see? That's how it works. This is hysteresis. And so if you give me a value of magnetic field and you tell me what is the magnetization you have there, well, if you let the system equilibrate, I can tell you what is the true minimum. But if you ask me what is the value for the physical system, it depends on the history, on the way you change the magnetic field along time, in time. Okay?
Yes.
All right, guys. So we are done for today. So let's continue then with the cluster expansion next time. Okay? So be prepared. It's going to be quite heavy in terms of calculations and also conceptually. Yes.
Actually, I have another question related directly to the lesson.
I have now I have to go and to take my daughters at school.
Oh,
So,
okay.
but if you
I
want,
mean,
we can.
it's really short, so
Yeah. Okay. So ask me then
I
if it's
mean,
really short.
so I saw the book that you recommended us before about the statistical field theory. It's an advanced stuff, but I saw some of the materials you teach us here inside the beginning of the book. So I think
Exactly.
so I think shouldn't that book be readable for us if we follow
The first two chapters are definitely readable for you. Only the first two chapters.
Oh, so you're saying that after the third chapter, and so we cannot
Well,
read it.
then at some point it starts with statistical field theory. Essentially, the first few chapters are readable. It's essential. You will find essentially what I told you, but then it starts with the beta ansatz, with the conformal field theory and other stuff that is
I mean,
beyond anything.
Conformal is chapter 10, so I don't know.
Well, so tell me the title of chapter 10, I will tell you. Do you have it with you, the book?
Wait, the title of chapter 10 is conformal field theory?
Yes. So
Yeah,
it's not, believe me, you will not understand anything there.
I mean, if I read it like by order, can I actually go through it? So, like per chapter.
If you read it by order, if you read it by order very slowly, in a few years, then you will be able to go through it.
Oh, okay.
But look, it's like everything. You have to learn things step by step. It's a very interesting book. It's very useful, but it's very advanced. Okay? It's really advanced. So you will be able to understand the first few chapters, which is elementary stuff, what I taught you here. But then at some point it starts with renormalization group and field theories and conformal field theory, and then it starts with the form factor expansion and beta ansatz and thermodynamic beta ansatz. All of this is like, do you know what is the renormalization group?
No.
No. So you see, the renormalization group, I give an entire course at CISA on the renormalization group, just on the renormalization group. And look at in which chapter is the renormalization group. I think there's only one chapter there about the renormalization group. And I gave an entire course about it.
Yes, it's only on chapter 8.
You see, it's only one chapter there. So I can tell you that at CISA, I give one course on the renormalization group, and it's a 20 lecture, it's a 15 lecture course, from 15 to 20. So it's a big subject, and it's only one chapter of that book. And you have to understand the renormalization group in order to read that book. Otherwise, you don't understand it. And it's only it's 20 lectures. So that's what I'm telling you. You can go through it, but very, very slowly if you want to understand things. Otherwise, you will not understand anything. So be patient.
Thank you,
Do things
Professor.
systematically. Okay, so I'll see you next time.
Yeah, see you.
Bye, guys. Bye-bye.
Bye, Professor.
So who's going out?